Our next presentation will be given by Professor Enrique Castro Rodríguez. He is an associate professor at the Department of Applied Physics and Naval Technology of the Polytechnic University of Cartagena, Spain, and coordinator of international master programs of the Technical University of Cartagena. He conducts research on heat transmission, structural vibrations, and acoustic emission, and collaborates intensively with industry in these fields. He will tell us about the application of physics to some practical and engineering problems in his presentation named Applied Physics in Civil Engineering, Acoustic Emission and Cool Pavements.
Have to do something?
Sure. Excuse me?
You should be there. Yeah? Is that you? Is that you? Yeah. Oh, it's not showing.
It's not showing on the screen.
Is it your presentation?
Yeah.
Okay.
Oh, no. No, it's okay. Well, thank you very much. It's a pleasure for me to be here celebrating this anniversary of the Faculty of Civil Engineering. And I would like to congratulate all the, and thanks to the previous speaker, because the conference has been very interesting and inspiring. I have been learning a lot from many disciplines, and I would like to thank to the organizers to make it possible. My field of expertise is applied physics, so I would like to present here some application of this applied physics and some relationship with applied physics and civil engineering. So I'm going to present two of them, which are, the first one is acoustic emission, which is a non-destructive method that, I think it can be applied to every part of engineering, but I'm going to concentrate it on civil engineering and regarding to the health monitoring aspect. And another very difficult application where my research group is working to is about curved pavements, which they are being developed as a solution to the urban heat island effect. This is an effect that makes that temperatures in cities are higher than the rural surroundings. So it is a possible solution to try to mitigate this effect. But apart from this application that are very specific, I would like to result that the use of applied physics in different fields requires a collaboration from the scholars for that field. For example, I'm conducting research in soils now with some colleagues from the Faculty of Civil Engineering in Cartagena, and I need them because I'm not able, I don't know nothing about that, so to apply this acoustic emission technique, it's necessary to collaborate, and they don't know nothing about acoustic emission and only a little about physics. So working together is possible to get much outstanding result and work on very novelty problems that can be solved by only some kind of scholars alone. Well, first of all, I'm going to speak about the acoustic emission technique. I don't know if you are aware of it because it's not very well known. It is, it is a technique that is based on the measurement of the release of strain energy inside a material. But the name can be a little misinforming because we are not measuring on the acoustic range. We are on the ultrasound one. So we measure waves between 20 kilohertz and 2 megahertz. Okay, so in some ways similar to ultrasonic testing, that may be some more popular technique, but the main difference is that now we are only measuring the waves that are produced spontaneously. We are not introducing an ultrasound and receiving it. We are only listening what is happening there. So it makes that this technique is a passive one. So it's not, you only are measuring what is going there, but no, you are not applying anything to it. Sorry. Well, how it is about? Well, you have a process that is happening inside your material, inside your structure, inside your sample, and then this process emits some kind of ultrasound, and you're registering it. It can be very useful to monitor how this process is going. It's very useful to monitor dynamical processes that are happening inside the material. But it has a problem, that it cannot be repeated. If you have a sample and you make the same thing, you are not probably measuring the same waves, because all the generated processes are irreversible, so when you are carrying out an experiment, it's very difficult to repeat it and obtain the same result. Its techniques can be used in many different things, but it has some property that it can monitor a structure during a long period of time. So it can be very useful to use it as health monitoring method, and structural health monitoring that can control what is happening, how is the health of the structure during long period of time. So if you have a critical structure like a bridge, like that, then you can get it controlled. I have said something before that is not very true. That is the ultrasonic waves that we are measuring here are spontaneous. They appear alone. That's not true. You need an external stimulus over your sample, over your structure, to measure something, because you have to induce the internal process. It can be, for example, to apply a stress or a thermal stress or something like that. But when you are carrying out structural health monitoring, usually the external stimulus is the ambient condition. The ambient condition degrades your structure, makes it to be corroded, or produce a crack there, and then you can measure the ultrasonic wave, the acoustic emission that is being produced there. Here, we have an example of things that we are recording. This is a typical acoustic emission signal. They are called burst type signal. It's characterized by a sudden rise of the amplitude. Here we are measuring the voltage. And then after that we have an exponential decay. Here we can see the typical parameters that we have to consider when working with acoustic emission technique. That is the arrival time, that it can be useful for localization, and it's the time that when the wave arrives to the sensor, the duration of it, the rise time, the time to get to the peak amplitude, to the maximum one, and of course the amplitude of the heat that give us an idea of how strong is this has been this emission. But acoustic emission has a problem. That is, this has a very low amplitude. It is necessary to measure very, very, very little displacement. So at the end, we need sensors to be very sensitive. So this make us to record many things that are not that we want to measure. For example, we can measure a lot of electric noise, as you can see here, which is something that is not happening, just electric noise from the environment, from the equipment. Or you can measure waves from other sources that are not the one that you are that you want to take into account. Well, now that you have an little idea of how this technique about, or how you can use it in civil engineering. You can use it in two ways. First, the most obvious one is to monitor internal processes. For example, if you are developing new concrete materials, then you can try to monitor or to inspect what is happening inside your sample. Or maybe if you are carrying out a soil test, you can try to identify what are the mechanisms that are happening inside it. But the most used part of acoustic emission is to monitor the health of the structure. So I'm going to show you some of these examples of application in health monitoring of structure. The first one will be to study plastic deformation, after that cracking, and a little bit on corrosion, but in reinforced concrete structure. When we have to deal with plastic deformation, we have to take into account what is called the Kaiser Effect. What is it? Well, it is about the lack of acoustic emission when a load is applied until its previous stress level are exceeded. What does it mean? That if we apply a load up to, I don't know, 10 kilopascals, then then you decrease your pressure, your stress, your load, then if you want to have again acoustic emission, you have to raise this level. You have to go to 20 or to 13. Why is this happening? Well, it is because the acoustic emission is supposed to be produced only by the plastic deformation of a material. The elastic one, it is supposed that it's not going to produce anything. So when you apply a load to the material, to the structure, it's going to suffer elastic deformation, plastic deformation, and when you reduce the load, the plastic deformation obviously remains there, it's not going to change, but the elastic one too. And when you apply again and the same load, then no more plastic deformation is being carried out. So you are not getting any acoustic formation unless you produce more plastic deformation. Well, how it can be used to inspect a structure? Well, what you have to do is to inspect regularly your structure in between several periods of time. If it is any more, it's no added damage in that period of time, then we are not going to measure any acoustic emission. But if you receive acoustic emission, what it means? It means that some kind of damage has been occurred during that period of time, and there is some discontinuity on the structure, on the mesh and the material, and then there the concentration of the stress is going to produce an acoustic emission they are going to measure with your sensor. This is what is called tunnel corollary, that is the acoustic emission testing reverse damage during the preceding personal period. Another use of the Kaiser effect is when it is violated, when it is not being confirmed. When the acoustic emission is emitted during with an applied load that is below the previous maximum one. What it means? Well, because as the Kaiser effect has something that is considered universal, so if it is violated, it means that a serious damage is present on the structure. If you have a global emission from all the structure, it means that a lot of damage is there, and you have to be very careful of what is going to happen with it. It is called the Felicity Effect. that is the acoustic emission for lower loss than the maximum previous one, is a consequence of the presence of high damage. It is used, this effect, to try to quantify the damage of your structure by using what is called Felicity ratio, what is the ratio between the load on the first appearance in your current loading cycle between the maximum load in your loading history, so the maximum previous one. And it's obviously if any value of it, that is any value of the Felicity ratio less than 1 is always an indication that there is a degradation in your structure, which is increased as the difference of the Felicity ratio to 1. As it is lower, then more damage or more degradation do you have in your specimen. Another similar damage parameter is the current ratio. That is it's defined as the cumulative acoustic emission activity during the unloading part of your cycle, and compare it with the total acoustic emission activity during the whole cycle. In this case, if this parameter is higher, it means that more damage is present in your structure. And both parameters, Felicity and current ratio, can be combined to make a chart, or to use this chart, when we can see that depending on the combination of the values, we can classify the health of our structure. Another parameter that can be used to monitor how is going your structure is the acoustic emission energy. It can be identified as the part of the dissipated energy during plastic deformation that is released during the degradation. So if you measure it, you are measured with one sensor part of this energy that is being released, this energy is proportional, obviously, to the dissipated energy. So in some way, it's related to the degradation of what is happening there, of the plastic deformation. It has been found that it is true, and that there is a relationship almost proportional between the hysteretic stress energy in a construction, in one reinforced concrete specimen, and the cycle loading. Another interesting application of acoustic emission is to monitoring of cracking processes. It can be useful to localize them and to know how are they growing, to find what is the type of crack that is happening there, the size of it, and the general damage state due to this cracking. The first one that we want to do, localize where the cracks is happening. Well, it is based on the arrival time of the acoustic emission to each sensor. So you need at least 2 sensors to make a one-dimensional localization, because at the end you are measuring your localization based on the difference of the time arrivals. So when you want to make a localization, you need at least 1 sensor more than the dimensional localization that you want to carry out. So at the end, if you want a 3-dimensional localization, you need more sensors. And if you have avoid some localization errors, it is better to have at least 6. What are the main problems with the localization? Well, there are 2 physical aspects of the wave propagation that we must take into account, and they are going to difficult the localization. The first one is the signal attenuation. Any wave that is propagating is going to be attenuated by the material. And the other one is the dispersion. What is the change in it's different on the velocity of the wave depending on the frequency component. So your wave is going to get, is going to change, the waveform is going to change it. So maybe you are measuring an arrival time that is not exactly the real one that corresponds to the position of the event. Very interesting feature about acoustic emission, it can be used to know how is your crack, what kind of crack is happening there, are you having in your specimen. How can do you do it? Well, there are two kinds of analysis that you can do. The first one is moment tensor analysis, that is based on the first arrival time and the first motion amplitude, knowing where if the value of the voltage is up or down, you can in some way and combining it with the information from other sensors, you can know if this is a tensile crack or a shear one. But it needs at least 6 sensors to carry out this analysis, and sometimes it's not possible, maybe because the wave is not arriving to all your sensors, or maybe because you don't have money to have so many sensors. And then you can use another kind of analysis that is called parameter analysis, that based on 2 parameters that are defined that way. The rest time divided by the peak amplitude and the average frequency, which is the counts that you have in your heat, what is the number of crosses over the threshold that you have, divided by the duration of your heat. It's a way to measure the frequency, not very, how do you say it, academic, but well, it can give you an idea of how is the frequency of your wave, and it is, it is used to classify your crack. Another interesting thing is to know how your crack is, how is the size of your cracks. To do it, acoustic emission scholars use techniques that came from seismology. That is because I don't know if you get noticed before, but acoustic emission and earthquakes are very similar physical processes, because in both of them there is a release of elastic energy that is happening without any, I don't know how, human intervention. So there is a big difference of the scale, obviously. Here in acoustic emission we have very low amplitude and very high frequency, and with earthquakes we have very high amplitude but very low frequency. But the methods in seismology can be translated to acoustic emission and can be used to monitor the size of the fractures. Here we have an example of that one. It is the V-value method, that is based on the fact that the logarithm of events with a given amplitude has an exponential decay. So if we make if we take logarithms for this number of events and the amplitude, we get a linear relationship. When we have the slope of the relationship, what is the parameter V, what is used to characterize the cracks. It is used in seismology to characterize big fractures, and it is used here to characterize the small one. With a limit as its value is higher, it means that we have very low, many events of low amplitude. So we have what is called micro cracks, and if we have a lower value of B, of parameter B, it means that we have a lot of high amplitude values. So it can indicate us that we have there a macro crack. An interesting thing about cracking phenomena is that it presents multi-scale aspect. So it can be studied by using fractals or fractal methodology. It has been found that energy dissipation during microcracking propagation occurs in a fractal domain that is between a surface and a volume. And so the total dissipated energy during cracking is given by that relationship, where it is proportional to what is called fractal energy density, what is some parameter that it independent of the site, it only depends of the material, and to the volume of your specimen elevated to the fractal dimension divided by 3. This fractal dimension, as it is happening in a scale that is between a surface and a volume, it has a value between 2 and 3, and it has been found that this is used to be the double of the parameter V that we have seen in the last slide. And as the dissipated energy follows this relationship, the acoustic emission energy that you are measuring, and is proportional to the dissipated one, is going to follow a similar relationship. What is that is this one? When it is called now acoustic emission fractal density. And the main, the important thing is how to relate it. How you can relate this energy and this, in order to know how to, well, not to know, in order, okay, well, sorry, I have said this wrong. The important thing is that you don't know what is going to be this acoustic emission total that we are going to have, but if you take a reference specimen, if you have a construction and take a small part of it and go into the laboratory, induce cracking there by applying a lot, and you measure the acoustic emission energy that is happening there, you can relate your laboratory measure with the acoustic emission total energy that are going to get in your construction, and then you are going to know it. Then you know what is in this total, and use it as a damage parameter by measuring the total energy that you have measured at a certain time, at a time. So here you measure all the acoustic emission up to that time, divided by the total going that you're going to have, and then you can use it as some kind of damage parameter to evaluate how is your construction. Another thing that is very related with cracking is corrosion in reinforced concrete structure, because when the corrosion of the steel inside is going to increase its size by the corrosion, and it is going to induce some cracking processes around it that can be detected by the acoustic emission. Here we have a phenomenological model of how the corrosion loss are in steel, when we have 4 phases, depending how is related with the corrosion properties in each part. And it has been found that using a parameter from acoustic emission that is the signal strength, the cumulative signal strength follow a similar pattern, which indicates that this technique can be used to monitor the corrosion in this kind of structure. Using it, you can know how is in which phase your specimen is, and then you can try to use other parameters like the average frequency that we have seen before to try to identify in which phase you are now. Other different application of acoustic emission is crack detection in rail tracks. When you have steel. It is considered that acoustic emission is possible one of the only non-destructive methods that can be used to monitor online fracture creation in service rail tracks, because you can put your sensor and try to monitor what is going there during the pass of a train. It has been found that fatigue cracks can be detected by the increase of acoustic emission hits and the count rate under traffic loading, and by the variance in other parameters like energy, rest time, average frequency, that can be also indicators of the presence of cracks. As you can imagine, the main problem here is the presence of noise. If a train is passing through a rail, obviously it's going to induce some noise that is not because of the crack, it's only by its movement. So you need to filter the acoustic emission you are measuring. You need to use advanced denoising technologies like discrete waveless transform, things like that, to keep only the part of the signal that is related with the crack growing. Or maybe you can use another kind of filtering that using defining what kind of cracks are, what kind of hits are produced by the traffic paths, and then try to filter them, knowing its characteristics, amplitude, duration, rise time, or a combination of these parameters. Another application, this in pavements, is to monitor the thermal cracks that can be produced there due to the thermal cycles of high temperature, of high variation of temperature. To monitor this, it has been developed the concept of embrighterment temperature, what is the temperature corresponding to the high energy event about an energy threshold. So if you are measuring the acoustic emission energy events, and then and correlated it with the temperature. When you have the highest one, then you have this temperature that can be an estimation of at which time the cracking process is going to start, at which each temperature. If you have a periodical thread with different cycle of temperature, it has been found that the Kaiser Effect that we have seen before is happening here too. So if the difference of temperatures doesn't change, you are not to get any acoustic emission. But if you raise the temperature, well, if the temperatures rise or the difference of temperatures rise, then the acoustic emission will be measured. And also, Felicity Effect, and this is something interesting, has been found here, but with a special characteristic that is, it is now not relating with damage, but with some kind of a microcap self-healing of the asphalt, probably due to the adhesive nature of the materials. So when we have here acoustic emission, but prior with a difference of temperatures that are lower than the previous one, can be an indication of this self-healing. Well, with that last slide, I'm finished this little overview of acoustic emission in civil engineering. As I have said before, there are many other applications of acoustic emission in civil engineering, but I only concentrate or focus in that one more related to health monitoring. This new one, interrelationship between applied physics and civil engineering, is what is called Pavements. That is, is some kind of measure to try to avoid this urban heat island effect. What is happening in this urban heat island effect? Well, it is mainly it is due to the absorption of heat from sun by the construction material that we use in our cities. Concrete, metal, all these things absorb many heat, and more than trees or soil. And it is also there are not there are less the water doesn't go into the soil, so there is less evaporation. So it contributes to the presence of more heat in the city. Are the tall buildings, which are obstacle to wind and make that the sound can be reflected from each building to another. The emitted radiation heat from each building can be go to another building. There are also heat sources like cars and machines that produce heat. So there are many causes for this effect. And from the civil engineering point of view, well, we can try to use two solutions. The first one is to use less absorbent materials in roads, what lead us to the concept of cool pavements, or to try to design urban roads and streets in a way that the wind can flow more freely. That is making them wider, not making not so tall buildings, maybe some more, try to design a city more human. Well, so if we focus on the first solution, using cool pavements, how can we make pavements to be cool? How can we be not so hot? Well, the first thing is to make them more reflective. So they want them to absorb less heat. How can we make them more reflective? Well, by adding metallic oxide pigments, some kind of pigments in the mixture, so that you get some whiter asphalt that is more reflective. And it has interesting consequences, that it increases the urban visibility at night. So you will need less urban lights at night in your cities. Other option is to make them more permeable, so the stormwater can soak into the soil and pavement, and then the posterior evaporation of water can cool them. This is made by making them more porous, and it has unexpected consequences that is very beneficial. That is, there is a reduction of traffic noise due to the fact that the pavement has more holes on it. Here I show you an example of cool pavements. It came from a project that my research group is working, that is called Life Heathland. And we can see we have 6th Street on the city of Murcia, which is very near of Cartagena, that he can pave with this a new reflective pavement. And 4 monitoring towers have been installed in this street to measure the air and pavement temperatures, and to get now how is the effect on this pavement in a real condition of a city. Here we have an example of this new pavement after its installation. So what are the results? What are the effects of this pavement on the city? Well, the first one, the solar reflectance has been increased. It is about 30%, that is almost 4 times that the normal one. Here we have a thermal imaging of the new pavement and the previous one. So as a mean, we have that there is a reduction of temperature between 7 and 11 degrees of the pavement. That is the temperature of the pavements. But this decrease produces a decrease on the ambient temperature, now of the air that we are suffering, of around 2 degrees. It's not very much, but it's something. It's in a city as warm as Murcia. I don't know if you know it, but in summer is very hot. it can be something very important for the people who lives there. It also has produced a reduction of traffic noise of 3 decibels, which is something that citizens appreciate a lot. And we have an increase of the luminance of the street at night, of 150% than with conventional asphalt. Here we have a photo of one of these streets at night, and it's much, we have a more visibility than in a normal one. Okay, I have told you the good things. No, it reflects more, we are less hot, we have less noise, but it has a cost. I mean, the use of these pigments in the asphalt, it makes the material costs about 3 times higher than the previous one, than a normal one. So it is something that cannot be done without a previous study. In order to let the city rulers about how there will be the influence of this new pavement in their city, a simulation software of the temporal distribution on the air has been developed by my research group.
Enrique, please, we are running out of the time, so just a little bit.
Okay, yeah, no, it's in the, okay, the last one, almost the last one. Okay, the many processes has been introduced in this simulation software: incident radiation from sun, reflected from buildings. And here we have an example of or a comparison of this result from our simulation software from the experimental measure. Most of the time there is only a difference of 1 degree. In some places there are higher differences. We are well, not here, that we thought that they are due to individual events that are not taken into account in our model, like the pass of a cloud or the presence of a heat source near the metering station. That was my brief overview about well, first acoustic emission, and the last one showing you how is this cool pavement. I would like to focus more than in the particular application on the fact that they are examples of interrelationship between applied physics and civil engineering in a way that I hope it is interesting for you and you can inspire you for new things or new ways of collaboration between both these disciplines. I think that they are very good example of interdisciplinary application that get better results when scholars from different fields work together. You know, in acoustic emission, there are many kinds of engineers working together: mechanical, signal processing experts, physics, civil engineers, and in cool pavements, you know, it's necessary the collaboration of civil engineers, people who know about heat transmission processes, or material experts. So I would like to underline that in my opinion, the collaboration between especially from different fields is something that is very good, and we will try to work in that way. Thank you very much for your attention, and sorry for the...
Thank you. Thank you, Enrique, for your presentation. Now we will have the time for just one question, and then we can continue during the lunch break to discuss more. Are there any questions? No? Okay. Then we can... Oh, sorry. Professor Blagojević.
Could you...
Thank you for your presentation of how different kinds of techniques connected, and that there is a close relation between civil engineering and other applied sciences. I want to pose one question about acoustic emission. what is your opinion? How is going to, what is the main direction in development of that method? Is this new kinds of sensors and instrumentation, or it would be signal processing and data processing based on measurement, how they are today?
Well, the main purpose of acoustic emission is to measure the measurement and the analysis. So I think that in both things, in the sensor aspect and signal processing aspect, is going to, there is a lot of work carry on there, and I think they are going to advance on both of them. In the case of sensor, as it can be used as a structural health monitoring method, there are many, well, that is a field that is very interesting for aerospatial structure, like planes, something like that, because a structural fail there is something catastrophic. So they are developing sensors that can be put inside the structure. They are very thin, or they are using fiber optics sensors that they can be embedded inside the structure. Another thing is wireless sensors. Now with wireless sensor, well, this acoustic emission works in this range up to 2 megahertz. So the sample rate, it needs to be up to 10 megahertz. That is a lot of information that has to be transmitted. And wireless sensors, I'm not very sure that now can transmit so much information. Maybe they works more on the low frequency range, up to 100 kilohertz. So I think that in wireless sensor there is going to be a lot of work in the next years, and maybe we're going to achieve to have a proper wireless acoustic emission sensor.
Okay. Thank you. I'm now officially closing this session.